Okay, so good morning, everybody. Let us start the class today. We have a session to start the class, and today we are going to discuss about the antenna and propagation theorem, reciprocity theorem. So today is 21st, 2021. So let us see today what we will go to study on reciprocity theorem. We are going to prove the reciprocity theorem. And for proving the reciprocity theorem, we have already started proving it. And today we will complete the proof of reciprocity theorem. So further much delay, we start our proof. So we have two mesh topology networks. Let us redraw you the topology. Here is our Z of 1, 1. This is the I1, and this is the E12. So like this, we will start here, and here it will be coming here, and there we will do another type of reciprocity. Okay, and then we will start here. This is the impedance Zm, we named it, and here Z up to 2. And then we'll start here. Here is the current component, which is named as I2. That will be connected with this. So this will be like this, and this will be like this. So this is E of 1, 2. This is number 1. This is number 2. This is another node. This is here. So this is the terminals number 1 of antenna number 1. Terminal of antenna number 1. We have already drawn this topology. This is another. This is terminal of antenna number 2. Nulls of antenna number 2. Okay. So it is clear, I think, everybody. So this is terminal of antenna number 2. This is terminal of antenna number 1. So this is the equivalent T network. Equivalent T network corresponding to fault terminal network. Corresponding to fault terminal network. Sati Kumari, are you there?
Yes, sir.
और दूसरी कहाँ गया?
पता नहीं सर.
सबको मैसेज करो ज्वाइन करने के लिए क्विकली.
Okay, sir.
And this is another network topology. This is Z11. This is Z22. This is ZM. This is terminal number 2. Here I get EF21. This is second, and this is the first mesh. This is I current. So this will be following to this side. And this will be flowing to this side. Okay. So this is the terminal of antenna number 1. Terminals of antenna number 1. And this is the terminals of antenna number 2. Number 2. So this is the equivalent T network for the corresponding port terminal network. This is also same. So I don't like that. And from there, we have proved up to the mesh topology network. Last day, we are proving that. what we have proved that Z11 and Z22 are self-impedance antenna of number 1 and number 2, and Zm is the mutual impedance between the two antenna. 1, 1, is a terminal of antenna number 1 and 2, 2 terminals of antenna number 2. Now we apply the Kirchhoff's mesh law to figure. This first is figure A and this is figure B. So if I apply Kirchhoff's mesh law to figure number A, and from the loop, going to the next page. So applying right here, applying Kirchhoff's OFFS, Kirchhoff's mesh law, to figure 1. From loop 2, what we get? We get that Z of 22 plus Z of M into I2 minus Z of M into I1 equals to 0. So that implies what? That implies I2 equals to I1 dot Z of M by Z of 22 plus Z of M. Now from loop 1, what I will get? Z of 11 plus Z of M into I1 equals to Z of M, sorry, not equals to, it is minus of Z of M into I2, that is equals to E of I2. So by substituting I2 value, what we will get? We will get Z of 11 plus Z of M into I1 minus Z of M into I1 by Z of 22 plus Z of M equals to E of 12. So continuing this portion, today is 21/1/2022. So continuing this portion, what we get? I of 1 in third bracket, Z of 11 plus Z of M into Z of 22 plus Z of M minus Z of M square by Z of 22 plus Z of M equals to E of 12. That implies I of 1, if I multiply both, then I got Z of 11 into Z of 22 plus z of 1 1 into z of m plus z of 2 2 into z of m plus z of m square by z square m minus z square m by z of 2 2 z of 2 2 plus z of m. So that whole thing is equals to E of 1 2. So that implies I1 equals to E of 1 2 into Z of 2 2 plus Z of m by Z of 1 2 into Z, Z of 1 1 into Z of 2 2 plus Z of m, I take common. So there is Z of 1 1 plus Z of 2 2. Now substituting I1 value, we get what I will get? We will get equals to E of 1 2 into Z of m by no sorry E of 1 2 into Z of 2 2 plus Z of m into Z of m by Z of 1 1 Z of 2 2 Z of m common Z of 1 1 plus Z of 2 2 bracket close into Z of 2 2 plus Z of m. That gives us E of 1 2 into Z of m by Z of 1 1 into Z of 2 2 plus Z of m into Z of 1 1 plus Z of 2 2. Twenty-first, 1, 22, 0.3. So similarly, the current I1 in the meter of figure 2 can be obtained or by symmetry suffix 2 may be replaced by 1. And vice versa. And from the above equation, we can obtain current I1, that is I1 equals to E of 21 into Z of M by Z of 11, sorry, Z of 11 will be replaced, 1 के जगह 2 होगा, so Z of 22 into Z of 11 plus Z of M into Z of 22 plus Z of 11. So thus, clearly from I1 and I2 expressions, they are same except has the value of EMF, that is E of 1, 2 and E of 2, 1, according to the theorem, statement, the theorem is proved. Stop. If we prove E of 1, 2 equals to E of 2, 1, if I1 equals to I2, applying condition I1 equals to I2 will give us E of 1, 2 into Zm by Z of 1, 1, Z of 2, 2 plus Zm into Z of 1, 1 plus Z of 1, 2. That is equals to E of 2, 1 into Zm by, this is 1 into Z of 1, 1 into Z of 2, 2 plus Zm into Z of 1, 1 plus z of 2, 2. This will be 2, 2. Sorry. So we can write what? E of 1, 2 equals to E of 2, 1. So that is the proof. So this is very important. Those who are looking, please know this is very important, because this will be in your examination to prove the reciprocity theorem, and you have to prove it by using the mesh topology network. Okay, so that is the proof. Now, what is the application of reciprocity theorem? The application of reciprocity theorem are: number one, equality of directional patterns; number two, equality in directivities; number three, equality in effective lengths; and number four is equality in antenna impedance. Now, what are these means? What does this means? Let us elaborately discuss about these applications. So we are elaborately discussing about this. First point is equality of directional patterns. Okay, the directory patterns of transmitting and receiving antenna are identical. Or if all the media are linear, passive, and isotropic, and the reciprocity theorem holds good. That is the first thing, application of reciprocity theorem. First, what it states that the direction patterns of transmitting and receiving antenna are identical if all the media are linear, passive, isotropic, and uh, reciprocity theorem holds good. If this it happens, then the direction patterns of a transmitting and receiving antenna are identical. So we have a proof for that. So what is the proof? Proof is that and this is the dipole antenna. Is represented by D, and a and if I do the perpendicular on this, just a minute. Okay, now we will draw here. Another color, I'm using another color, so it will be understandable. It is Rx, okay, and the direction of this antenna is this here. This is another antenna. This is another node of the antenna. So this is V. This is test antenna. This is antenna number 1. This is antenna number 2. This is small dipole antenna. Okay. So this is the directional pattern measurement for a transmitting antenna. Okay. So how does it prove holds? Under the mentioned condition, it is to be proved that the transmitting and receiving antenna patterns are identical. For this, consider two antennas. Number 1 test antenna and number 2 and another antenna, that is number 2. So now antenna number 1 and antenna number 2 are the 2 test antennas. Okay. Let number 1 is transmitting and antenna number 2 is receiving. So this antenna is transmitting, okay, and this antenna is receiving. The pattern may be either field pattern or power pattern, which itself is proportional to square of the field pattern. So field pattern and power pattern is proportional to, power pattern is proportional to square of the field pattern. So power pattern is proportional to square of the field pattern. So field pattern this square. Considering field pattern, keeping the transmitting antenna number 1 at the center of the observation circle, the receiving antenna number 2 is moved along the surface of the great observation circle. Move along the surface of the observation circle. Now, if a voltage E is applied to the transmitted antenna number 1 and the result current I at the terminals of the receiving antenna number 2 is measured, which is indication of the electric field of the at the location of antenna number 2. If the process is reversed, that is the same voltage E is applied to the antenna number 2 and the resulting current I is measured at the test antenna number 1. This time the receiving pattern of the test antenna number 2 is obtained while previously to that of antenna number 1. According to the reciprocity theorem, from every position, the test antenna number 1, the ratio E of I is same as was in previous case. Thus, it proved that the radiation pattern of test antenna number 1 observed by moving receiving antenna number 2 is identical with the radiation pattern obtained when the antenna number 2 is transmitting and antenna number 1 is receiving. That is when the process is reversed. A variation of method may be used instead of receiving the measurement procedure. The resulting current of the probe antenna number 2 is measured at the new locations by changing the radius of the observation circle. It would be found that whatever may be the position of the antenna number 2, the ratio of E by I, that is, what is E? E is the voltage applied and I is the current applied. So E by I is always same, hence the proof of the statement. Understand? समझ गए? Hello?
Yes, sir.
Yes.
Okay. And number 2 is the equality of the directivities. The directivity D is defined as D equals to, equality of directivities. Next point. Equality of the directivity. So what is directivity? Directivity D is equal to maximum radiation intensity by average radiation intensity. So that is directivity. So if I do it mathematically, then we can write D equals to phi of theta plus phi max by phi average, that is phi of m by phi average. But as we know, average Ri equals to total power radiated in watts by 4 pi in steradian, 4 pi in steradian. तो फिर हम क्या बोल सकते हैं? हम बोल सकते हैं that is equals to pi of average equals to W by 4 pi. Watt by steradian SR. So by substituting phi of average value, what we'll get? That is equals to D equals to phi of theta comma phi max by W by 4 pi. That is equals to 4 pi into phi theta comma phi, that is the coordinates, max by W. But we know the total power radiated is given by radiation intensity. Radiation intensity, that is phi of theta comma phi, integrating over solid angle 4 pi. Solid angle 4 pi. Steradian, steradian. that is W equals to integration over 4 pi theta, sorry, phi, not theta, coordinates theta comma phi d of, so that is equals to d equals to 4 pi phi of theta comma phi max by integration over 4 pi phi of theta comma phi d. That gives you 4 pi theta phi fm integration over 4 pi, that is equals to 4 pi by double integration 4 pi by phi of m to d, where g is solid angle that is equal to sine theta d theta d phi. So we can write d equals to 4 pi by integration phi of n d omega, where phi of n equals to phi of n theta comma phi, that is equal to phi of theta comma phi by phi of theta comma phi max, that is equals to pi by phi of m. This is called normalized power pattern. Okay, so everybody please give your attendance. You have less than a minute. और एक बाकी है, हाँ ठीक है. सो इसके और एक छोटा सा पार्ट है, वो कल का क्लास में हम लोग करेंगे. उसके बाद इक्वालिटी ऑफ इफेक्टिव लेंथ और फिर ट्रांसमिशन एंटेना रिसीविंग एंटेना में ये अप्लाई करेंगे.